All right, you're welcome. Very happy to introduce to you this very special topic under wave particle paradox, and I bet you it's going to worth the time. So please stick till the end of this video. You are going to learn a whole lot because I'm prepared for this. Ladies and gentlemen, please don't forget to hit the subscribe button, share this video, subscribe to this channel, and at least give me a thumb up and comment. All right. As you can see, we have a question on the screen and under wave particle paradox. Before we go further, we are going to look at what is wave particle paradox and how it is very important that we learn it. All right, so in talking about wave particle paradox, I am going to call a few names who have been very, very vital in studying this, which is mainly under quantum mechanics, which is mainly for light, photon, and all the rest of them. So, wave particle paradox is a cornerstone of quantum mechanics and has several profound implications, just like I said, which is under quantum superimposition, uncertainty principle. Now that I've mentioned uncertainty principle, we don't have to forget the name that is very loud whenever we're talking about that is Heisenberg. Heisenberg. So please, I'm coming to the solution of the question on the screen, but before then, we have to water the ground. We have Heisenberg. Oh, sorry, I don't think that spelling is the right for this man. And we have to give some respect to his name. He really did very well. Heisenberg. So I'm going to start by Heisenberg. So the name is very profound when we are talking about wave particle paradox. Like I said, Heisenberg, Young slit experiment, de Broglie, or the one we call de Broglie, de Broglie. Most of you who are English inclined will want to call it de Broglie, but it's a French name, de Broglie. All right, so these are names that you will always hear when we are talking about wave particle paradox. So what exactly is wave particle paradox? And we are saying it is the idea that a particle can show, okay, let's say it's a wave particle paradox or wave particle duality refers to the idea that light and matter, when I talk about matter, I'm talking about electrons, have both wave and particle properties. Both wave and particle properties. So sometimes it depends on the context and how you use it. It's just like you looking at a human being. You don't know that this person is very, very versatile in some other ways, but you have been using him. Let me go into football. If you're a football fan, maybe you have been using somebody to play fullback, left fullback, but you never knew that this person can strike. So that is what happened in the early centuries, where they're looking at light only. They never knew that that light has a property of both wave and also as a particle. Light can behave as a wave and also behave as a particle. So enough of all the talk, because the talk is big. So many things we are going to talk about on this one. This video will not be enough for us to exhaust what we have. However, looking at the question here, I've talked about what is wave particle paradox and also talk about Heisenberg. I said Heisenberg said, we'll call it Heisenberg uncertainty principle. Heisenberg uncertainty. Heisenberg uncertainty principle. And Heisenberg uncertainty principle say it is impossible to determine accurately both the wave properties, look at that, wave properties, and then of matter and its particulate property at the same time. So you will not be able to know accurately the exact position when we talk about position, and at the same time also know momentum. momentum. In part 2, we are going to use them to solve. So according to Heisenberg uncertainty principle, the uncertainty in the position will lead to an uncertainty in momentum. And according to him, this is equal to what is called reduced Planck. This is called h bar or reduced Planck. And this h bar or reduced Planck is given as Planck's constant all over 2 pi. Alright? So sometimes we also say the uncertainty in energy can also lead to uncertainty in time. And also the same thing as h bar. We also say that the uncertainty in, let's say, position, and also leading to, I'm sorry about this, okay, so what is that? Why don't misbehave? Please remember, I have, if you look at the bio of this channel, you see join. For those of you who would like some one-on-one coaching on private classes, it is also very important to reach out to us. So uncertainty in the position and uncertainty in velocity is having this relation according to Heisenberg. So this is what Heisenberg said. Maybe we are going to be using these properties or these relations in our next lesson. But then what we are going to be focusing now is on this man, de Broglie, just like I mentioned earlier. De Broglie. Okay, let me clear some part of this to have a very good space for us to do our work. Okay, I'm cleaning here as well. So when we are talking about de Broglie, what did he say? I don't want to go into too much thing about de Broglie. Maybe you have a little history about him. De Broglie said that whenever an electron is moving, that the electron moving is going to have velocity and momentum, but momentum is mainly called as p. So that means no, let me put it this better. I'm going to say that an electron moving, remember electron has mass, that it also has what? Velocity. And if electron has mass and velocity, that means is related by this lambda is directly proportional to, is inversely proportional to the momentum. That is what de Broglie stated in a very simple term. So de Broglie was saying that the wavelength of a moving particle with its momentum and thus establishes the wave behavior of matter. So because a moving electron has that particular velocity and also has what do you call it, a wavelength, then that particle must have been a light, because light has wave. Light is a wave, and light has properties of wavelength. And if a particle will have mass and velocity, then it should have wavelength. That was exactly what the man says. So we want to ask ourselves, who is this de Broglie? Mainly called Louis de Broglie. Louis de Broglie, most contribution to physics, in his theory of wave-particle duality, proposed that in his doctoral thesis in 1924, at that time, the nature of light was already debated, with evidence supporting both wave-like and particle-like behavior. De Broglie extended this idea to matter, suggesting that particles such as electrons could also exhibit wave-like properties. He introduced the concept of the de Broglie wavelength given by the equation. So whenever you have this equation, this is the lambda is equal to h all over p, and this p is momentum. This is the Broglie relation. This is de Broglie's equation. Very important. If you're a Waec student, Waec will always ask you to mention whether that is de Broglie. Not just Waec, many exams they want to test your understanding of knowing the equation according to de Broglie. Now, I think we've tried to pour a lot of water on the ground, so we can now go ahead and solve this question we have with us. Now the question says the mass and wavelength of a moving electron are 9. Let me see. The mass and wavelength of a moving electron are 9 times 10 raised to the power minus 31 kg and 1.0 times 10 raised to the power minus 10 meter respectively. He said calculate the kinetic energy of an electron. Now kinetic energy has come in, so we need to do a few of mathematical analysis in order to bring the Broglie into that relation. But remember this is kinetic energy. When we talk about kinetic energy is giving us half mv square. This is kinetic energy. We also know that according to the Broglie, lambda is equal to h all over mv. So you see, let me highlight this for you to be able to look at this. This is the mass is here as well, and mass is here. So with this understanding, we are going to combine these two equations and to have a bearing. So let's keep going. So let me first of all find the, let me look at, if you look at this, we are given the distance. We are given a distance. So I can find V, and also if you also look at this, V is at this point and also V is here. Go ahead. So, and according to this, I'm going to say that, remember, let me just make it very clear for you. If you have the lambda is given as 1 times 10 raised to the power minus 10 meter. That is the lambda. Because lambda is measured in meter, so you must know that. So I'm going to have, let me put this in my blue color. I think it's my favorite. All right, I have, according to this equation, I'm going to be dealing by, okay, let me put it here. 1 times 10 raised to the power minus 10 is going to be equal to, and remember the h there is the Planck's constant, is already given in the question. If you look down on the question, you see the Planck's constant, which is 6.6 times 10 raised to the power minus 34, all divided by mass. We were given mass, which is 9.0 times 10 raised to the power minus 31. Then I do not know the velocity, so the velocity is there. So a very clear illustration, I'm going to say that velocity is going to be equal to velocity. Okay, velocity is going to, if I clear the fraction, you know, people like to say cross multiply, and to me that is, I don't know. All right, so I'm going to say, I'm going to have 6.6 times 10 raised to the power minus 34, all divided by, 1 times 10 raised to the power minus 10 times 9.0 times 10 raised to the power minus 31. So V is going to, when you clear the fraction very well, simply say 6.6 divided by 9. It must be very high. It's an electron, it's wave, it's light. All right, so, and I'm going to have that this is going to be 7.33 times 10 raised to the power, that should be 6 meters per second. So I've gotten the speed. The next thing I have to look for is the energy, because we are looking for the kinetic energy. So I'm going into this equation and substitute this V for the value, which is 7.73, and do the rest of the calculation. All right, so please, if you have watched this video to this point, they are not holding your hand, just hit the subscribe button to support this channel, and also hit that like button. All right, let's go. I'm going to, let me go back to black. Excuse me. So kinetic energy is going to be equal to 1 all over 2 multiplied by m, which is mass. and mass is 9 times 10 raised to power minus 31, then times, this is half mv, which is 7.3 times 10 raised to power 6 all squared. No, don't act up. All squared. All right, so a very careful simplification of this or evaluation of these terms, we are going to have that v is going to be 2.42 times 10 raised to power minus 17 joules is the energy. Joule is the energy. So what I did was just just divide this 9 divided by 2 is going to be 4.5. 4.5 multiplied by 7.3, I think 33, I'm going to have 4.42 times 10. Then this is going to be 6 times 2 is going to be 12. So it's going to be 12 minus 31 is going to be 17. Ladies and gentlemen, this is where we draw the curtain for this one. Thank you for staying till this point. Have a nice day.